Okay, cool. Yeah, so I'll be taking you through what the challenge I set up for Hack Fridays, I think last week. Um, and it wasn't a difficult challenge, to be honest. It's actually a challenge I stole from another CTF and then modified it. And then I put their walkthrough as a free hint. And yeah, it wasn't that bad anyway. Let's see. Okay. And in case at any time you don't see my screen, please do tell. So CTF, I mean, it's like creating challenges has become a hobby. Like, as for this month, I've created almost around 20 challenges. There was BAC DEFCON, there's B-sides, then there was Cyber Olympics, the quals and the finals, and there's one I'm creating for some other CTF in Nigeria. So it's crazy. Oh. But it's cool. But it's just that sometimes I lack ideas, and when I lack ideas, it gets hard. Like now for this specific challenge, I didn't have an idea. Like Koimet told me like we need to create a challenge for for this Friday, like 3 challenges. So like one per person. Like normally we have like so per week there are people who create. So like it was now like our turn. So it was me, Koimet, and Oste. So I was just to create. I was like, huh? I don't have an idea, guys. You guys got me like off guard, like seriously. So I remember playing some CTF, and there's a specific challenge that I found so interesting. I was like, I could just modify it and then like have it as the challenge, and that's exactly what I did. And I didn't hide because when you look at this challenge, the hint here, I literally said, um, check out my pals walkthrough of Flock of Seagulls from Sunshine CTF. I mean, yeah, so it was from Sunshine. It was a child called Flock of Seagulls. And I really enjoyed it because I've honestly never seen such a challenge before. And it was fun doing, like, yeah. Also, you guys should go subscribe to this guy. He's Sloppy Joe Pirates on YouTube. He's a good friend of mine, also way smarter than me. Let's see. I could just have clicked the anyway. Oh, Sloppy Joe Pirates. Yeah, this dude. So just search Sloppy Joe Pirates, or I could also just share his link here later. Yeah, he does walkthroughs for. He tries to do like any CTF that he finds. He says it's fun. So yeah, lots of walkthroughs. Yeah. Okay, cool. So this was the challenge, and you're given a file. You know, you're given a zip file, So we can, I guess we could just download it. Mm, okay. Is it always this slow or it's just me? Again. Oh, one sec. Maybe it's me. Now I'm good. I'm good. I'm good. Okay, maybe it's just the CTF room. I don't know. So, is it gonna finish or I just leave it because I'm the one who uploaded the files either way. Yeah, I guess I could just leave it, but I hope you guys are hearing me okay because I really hope it's on my net. Which I know it isn't, but I hope it's not. Um, so inside the zip file you'll find this binary, I believe. And if you do a file on it, you'll see like it's a 64-bit binary, you know, x86 64, that's for the 64-bit architecture, and it's statically linked. So it doesn't rely on libc to for dynamic linking of like functions. So it's just like it's an independent binary. Like it will run on any version of Kali, of Parrot, or CentOS, whatever. So yeah, and I did that because I didn't want guys having the issues with like libc and stuff. So I decided to statically compile it, but it has its downsides, which we'll see in a bit. Um, if you run it, actually, let's run checksec. So checksec. So this checks like the protections on the binary, right? So we have partial rel row, which means you can edit got entries, and there's a canary. Well, depends. I mean, not the usual canary, but yes, there's a canary. Then NX is enabled and no pi. Okay, NX enabled means you can't execute shellcode on the stack, and no pi just means like addresses are not randomized in the binary. So like you know exactly where addresses are in the binary. So okay, you can open Gdraw um, and have a look. So nested, there you go. So now we are decompiling the binary and trying to look at the functions and what they do and stuff like that. So like I normally use Gdraw. You can use also IDA, but IDA is not a favorite of mine, so I prefer Gdraw. Um, yeah. So, oh yeah, I was talking about the downside of compiling it statically as much as it can run on any sort of architecture is this. It takes a while to decompile. Since like it's an independent binary and it doesn't depend on libc for like dynamic linking of functions. Actually, like okay, one major difference between statically compiled binaries and dynamically linked binaries is um, the dynamic ones are smaller. And they're smaller because like they don't have to like how do I put it? They don't have to glue all the functions into the binary. They just glue, let me say, pointers, sort of. So like you'll see like a puts function in the binary, but it will rely on libc for the actual address of puts. Like it's using the puts from libc, not the puts that is in the binary in short. So yeah, that's one major difference. So like for this one, like everything is there. That's why it takes a while to decompile. So also that means when you're going through the binary, not everything is what's it called? Not everything is necessary. Let me put it that way. Like you don't have to decompile everything. So it's just you start with the main function. Actually, this is the reason. This is the reason I had this question here. What is the address of the win function? That's the reason I had this question. I had it cause since there's so many bloated functions inside the binary, like it would be hard to know that there's a win function, Like how would you know there's a win function? So that's the reason I had that there to act as a hint again that there's a win function. Um, yeah, so let's give it a bit to decompile. Yeah, and it's done. Okay, cool. It's funny, it has landed me in main. I don't think that happens. Or does it? I don't know. So this is the main function. The main function is the function where the binary starts executing, I guess. Okay, it starts from entry. Actually, in dynamically linked binaries, it's more of entry. So that's where the binary starts. Then in entry, there's a function in libc that calls the main function. It's called libc start main. Yeah, so that calls the main function, and then now the main function executes. But for this one, since it's statically linked, we don't have such. So it's just main. I guess there would be entry, but then let's see. Actually, let's see. Let me not jump into conclusions. Does it even have entry? It doesn't have entry. So yeah. Um, cool. So in main, we have this setup function. This one just prevents like buffered outputs. And we have this puts call. So this prints text on the screen. So it says, I'm a simple fun challenge and my aim is to put your basic knowledge of the stack to the test. And that is what you see when you run the binary. Yep. And then it calls func1. Then in func1, we see there's a long here. And then it calls func2. And then when func2 returns, it checks whether the return address points to func1, because you see, like this is checking if this address. So like, well, uh, let me open the original challenge. Then at least you can have an idea of what this challenge is about. So it was called flock. Actually, if if you look at the original challenge and this one, you can't really see the difference apart from this. So I pretty much cloned the original challenge. Like there's no other difference. Also, the original challenge is as dynamically linked binary, not as statically linked. So you can see the functions are just this one's, not as many as this one's. They even put in folders. So sort of, yeah. So for this one, the original challenge, it calls func1, then func1 calls func2, and then you see that sort of check like the one we've seen here. So you can see they're exactly the same. There's nothing different. So yeah, well, so this one goes all the way to func 5. Like each function calls the next, and so on and so on. So this is the last function, func 5. And also this one has that check to so basically, okay, this check just it's checking to see if you're returning to the right function, as in it will check the return address. So normally in like phone challenges you'll see like a canary, but for this one it's a bit different. This one it's like, for this one it's more of like, I won't put a canary, but then I want the flow of the program to make sense, like I don't want you to, as in, as much as there's an overflow here, and there's an overflow because we are reading 500 bytes into a 112 byte buffer. Like as much as there's an overflow, I don't I don't want to put a canary. I just want to ensure that the flow of the program is as is, like it hasn't been corrupted. So that means as much as you have the overflow, you can't really do much with it, because if it checks the return address and sees like you've corrupted it, then it will call fail, and fail just echoes fail. Yeah, that's so this is the original challenge. But you can still have a look at it a bit more before we jump to mine now. So, as I've said, the main function, right, calls func1. This is another difference between the original and mine. So in mine, you can see func1 has the check, but in the original, func1 doesn't have the check. It just calls, that means in the original challenge, if you return from func2, you can return to any other function that you'd want. Like there's no check. But in mine, even after returning from func2, there's still a check, so you'll have to return all the way back to main. But for this one, the minute you get to func1, you can return to, the win function, because this also had a win function. Um, yeah, so func1 calls func2, func2 calls func3, func3 calls func4, func4 calls func5. Okay, so okay, so first things first, you have a pointer to the buffer where you're reading your inputs. And I know this because you can see the read call here. Okay, we can rename this actually to something else. Let's rename this to in buffer. So we are reading 500 bytes into in buffer. You can see in buffer has a size of 112 bytes. I can actually change this to char 112. Yeah, that looks much better. Awesome. Problem is we've lost the pointer. Yeah, that's the problem. But anyway, so what was I saying? Yeah, so like we're reading into in buffer. In buffer has its array is 112 bytes. So that's as much as it can hold. So you can see there's this variable local10 equals in buffer. Whenever you see such a thing, it just means it points to in buffer. So when this printf is executed, song begins at this. So this prints a pointer. It will print the address of in buffer. It's a classic. Normally, sorry. Normally, when you see such in a pawn challenge, normally it's usually like it's a typical like you're reading in shellcode and then you know the address of the shellcode, so you just jump to it. But for this one, that's not the case. You just get the address of um of the buffer that you're reading to. But since NX is enabled, then you can't place shellcode and jump to it. You wouldn't be able to jump to it even if it was NX disabled, because there's a check that checks the return address. Because at that point you'd be returning to the buffer since you placed the shellcode there. Okay, so we know this is a pointer to in buffer. Okay, and at this point it prints the address of in buffer. Okay, so and then it prints pawn me, and then it reads 500 bytes into in buffer. So at this point we have a buffer overflow. Okay, so we have a buffer overflow, but then we can't really do much with it because there's a check that checks the return address, yeah, yeah, that's pretty much the chal. So if you watched the walkthrough that my friend did, basically you're supposed to ensure the program flows as it's supposed to be, like as it's supposed to flow, and at some point you'll get a leeway to jump to some other function because there's no check. Okay, so this is the original challenge. So now in my challenge, func1 calls func2, func2 calls func3, 3 calls 4, 4 calls 5, 5 calls 6, 6 calls 7, 7 calls 8, 8 calls 9, and 9 calls 10. um yeah, so yeah, as much as I copied the challenge from some other CTF. I didn't want it to be as straightforward as because literally, if it was the same 5 functions as the other challenge, like the original challenge, it would be very easy to watch the walkthrough and just change the values and then solve it. But for this one, I just decided to add like five more functions. So like now there are 10 functions. Um, cool. So this one is just the same as you saw in the original challenge. So let's see. Okay, so in mine though, I didn't place a pointer to the buffer. I just pretty much, like, what's it called? I just printed out the address of the buffer. Like I didn't see a need to put a pointer to the buffer, then print the address, you know? So yeah. So what? Yeah, so after printing the address of the buffer, it's, you know, outputs tell me all about the stack, and then it reads, this is 512 bytes into a 144 byte buffer. So there's a buffer overflow. But then again, as in the other challenge, there's a check. So it checks the return address, and if the return address isn't equal to this, it will call this function, and this function just says invalid ret, and then it exits. So the program dies at that point. So yeah, what else? There's something else I feel like I wanted to say. Oh yeah, so basically this check, as I said, it's just checking to see if the return address is good, like it points to the previous function, if that makes sense. As in, as I said, the program should flow as is. Like there shouldn't be any like corruption or anything. So when func10 returns, it should return to func9. Then when func9 returns, it should return to func8, and so on and so on and so on. So that is what the check is. The check is actually, so this address is an address in func9. Let me show you. So you see this 401.83, and we have here, where is it? This is, oh, this is the win function. Oops. So let's go down. 401.8D3. There we go. It's this one. Here it is. So, oh shit. Let's see. Func10. Yeah, so as you can see, for 183 and in func9, we have that address. And that address is immediately after the call func10, because that is where the function returns to after func9 has called func10, if that makes sense. As in, let me see if we can have like, so like, the sort of like the flow is like, func1, then func2, then func3, then func4, func5, then func6, func7, func8, func9, then func10. So this is what's happening. So for example, func9 is calling func10. So when func10 returns, it will return back into func9, like as in here. So like, so this is func9, and so it calls func10 at this point. So the minute it's done with func10, so this is the instruction that called func10. So it will return here, like after the call func10. So it returns back to func9, and then it also checks whether func9 is returning to func8, and so on and so on and so on. So you'd have to make sure the return address is as it should be for all the 10 functions, func1, func2, func3. So like for func1, you have to make sure it's returning to main. See this one? And if you check main, so this is 401B04. And this one, we have that here, 4010B4 right here. So you see main called func1. So when func1 returns, it will return here at this point and continue. So that's the whole idea of the challenge. Now the problem comes in, as much as you are doing the buffer overflow and making sure everything is at its place, there is no way that you can do the buffer overflow and make sure everything is at its place, and at the same time jump to another function later on without messing the stack, as in without, how do I put it, without interacting with the stack. Let me put it that way. Because if you let the program flow as it's supposed to flow, then you don't have a leeway to um, you don't have a leeway to control the program's flow at whatever point, you know. So this challenge was very simple. So if we look at func10, okay, we know we have an the address of this buffer, and that's what is printed here. This address here. This is a stack address. You see the 7FFF. So that's a stack address, and that's the address we get here. So for the, like, it points to where we are reading our input, our 512 bytes. So yeah, so the logic behind this challenge is, let me show you. So if we run this, break at func10, run, then let it set up the stack, then maybe check here. So it's very, very simple. Let me actually have stack 70. So this just shows you how the stack looks like at this particular point in time. So you have the base pointer. Now the base pointer, of course, it points to the base of the stack, you know. So like, imagine the stack as a rectangle, then down there we have the base pointer, you know, where, you know, like we have the feet, we have the legs, and then up there we have the head, or the stack pointer. Okay, so actually, wait, it should be the other way around, but let me just explain it that way first. Okay, as of now, I have one hand on the desk and the other one is just above it, so I'm sorry you can't see that. But yeah, so like the hand on the desk is is the base pointer, and the hand that is hovering above it is the stack pointer. But ideally, you know, the stack grows downwards, so it should be the other way around. So now we have the stack pointer on the desk and the base pointer hovering there. So um, let me explain something here. So like we do this as main, you can see, so this is how the stack is set up. Let's actually do func1 to make it make sense a bit. Yep, cool. So it does a push RBP, so it pushes RBP on the stack, then it moves RSP into RBP. So the value of RSP is moved into RBP. So we have our RBP there, and then it subtracts 16 bytes from RSP. So from where as much as you're saying the stack is going downwards, there will be like a length incrementation of the stack size at this point when it does the subtract, you know? Because um how do I put it? Yeah, because like we are subtracting, as in it's going downwards. So like we're like, instead of it not making, like, making sense, since we interchange the values, now it's like sort of incrementing the stack. So now the stack is 16 bytes long, if that makes sense. So the same thing, so like I wanted to explain that because of this. So ideally, we have our base pointer. So this is the current base pointer in func10 stack frame. So what you'll notice is the value of the base pointer is a pointer to the previous stack frame's base pointer. Okay, so yeah, so as in the value of the base pointer at this point is the holds the value of the base pointer in the previous stack frames. Yeah, you know. So what I mean by this is the base pointer of func10. So this means this is the base pointer of func9. Then this is the base pointer of func8, then func7, then, you know, so on and so on. Then, as you know, the return address sits at RBP plus 8. That is something very fundamental that you should know. So You can see that actually it actually says it here, but let's walk through it like this. So this is RBP. Then you can see we added 8. Then we get the return address. And this return address, as I said, it points back to func9 because func9 is the one that called func10. So when func10 is returning, it returns to func9. And you can see the return address is pointing to func9 plus 22. So at that point in func9, so func9 plus 22 is where func10 returns to, ideally. And you can see the same pattern goes on and on. We said this is the base pointer of func9. And you can see that's what we have. Then you add 8 bytes, you get the return address. This return address points to func8. Okay. Then as you can see, this is the base pointer of what is it? Func8. So if we check here, that's what we have. Add 8 bytes, we get the return address. So that's pretty much what the child is. Like you just have to, as much as you're corrupting the stack, like now for example, if this is where we are reading to, because this is the stack pointer, we can read, like, as in we can write all of this because they're not important. Like we write all the way down, and then when you get here, we assign its correct value, and 8 bytes from this, we assign the return address, if that makes sense. Okay, cool. All right. So yeah, that's pretty much the child. So like for mine, unlike the original one, you'll have to get to, so the minute you get to func1, you still have to make sure that it returns to main. So this is an address that's pointing to main. So if we check main, so let's see, main. Yeah, so you have to return after this call right here. So this is where func1 returns to, right here. So now with this return, now you can return to the win function. Let me show you the win function right here. Yeah, so it just does an execve message, so just spawns a shell in short. Okay, cool. So, all right. I guess we have. I guess I hope like I've laid out the whole sort of challenge. Like you can play with the stack, but you just have to ensure like all the values are in place. In short. Okay. And I think the other thing would be the fact that as much as you want to assign the value of RBP correctly, when you're assigning its, like the value, you do note that whatever value you assign is the value of the next or the previous stack frame, if that makes sense. So what I mean by that is this. This is RBP, and this is its value. And this value is the value of func9's stack frame, like the base pointer. Okay, so the minute you do the buffer overflow and you reach this point here, you need to give it this value and not this one. And the reason is cause if you check like let's do this as func9, this live rate. So what live does is let's see. Okay, so a live rate ideally does a move RBP into RSP and then pop RBP like this. This is essentially what live does. So what does that mean? It will move the value of RBP into RSP, then pop that value into RBP. What that means is whatever value is moved from RBP into RSP, that's the value that will become the new base pointer. Okay? So that's why I'm saying, as much as you're like ensuring the values are where they should be, RBP needs to be like the value itself, not the current value. If that makes sense. Uh, yeah. So like, if this is our RBP, this is the value that we give it. In short, okay. So yeah, that's pretty much it. Um, Yeah. So, for example, if you give it the wrong RBP, then when it like now, for example, when func10 returns to func9, you can see the immediate instruction executed when it returns involves RBP, and it's actually looking for like the value of RBP. So, like for example, if you set RBP to 0 and it executes this instruction, it wouldn't make sense because 0 isn't a valid address and it's looking for a value from RBP, if that makes sense. Okay, cool. Let's write the solution. Maybe it will make sense. Um, okay. So we don't need libc. Cool. So we actually have the first question that I left here, which is how far is the stack variable from the base pointer in func10 stack frame? So it's very easy to check that. Normally I'd use like Jidra. So like are we in func10? No, that's when. Yeah, this is func10. Great. So we have so this is our buffer, this one, the 144 bytes. Now, as I said, RBP plus 8 equals ret. Like that's where the return sits, right? RBP plus 8. So ideally, quick math, um, so RBP plus 8 equals ret. That means RBP would be ret minus 8. Great, right? Simple, you know? Okay. So if that's the case, if RBP is what? Is ret minus 8, then we can calculate the distance between local 98 and the return, then subtract 8, right? Because if we get the distance from here to the return, and then minus 8, that would be our RBP, okay? So normally in Jidra, what this means is it's exactly OX98 bytes away from the return, okay? So if we check sorry, OX1, OX98. Yeah, that's, wait, was it 98? Yeah, 152. So 152, you minus 8, and you get 144 bytes. I hope that was the answer. Yeah, I really hope so. Um, I honestly don't, because because I remember in the other challenge the value was 128 because they're not as similar because you can see this the size of this stack variable is 144, and from that challenge the stack variable was can I really remember? Let me see. I think it was like 120 or something. Let's see, or maybe 136. So yeah, 112. Damn, I was far. Yeah, so for this one it was like OX88. So OX88, then minus 8, 128. Yeah, exactly. So yeah, so for this one we know the value is 144, right? So that was the answer you're supposed to get here, and I think like multiple people at least found that answer. Um, yeah, so how far? Good, awesome. So, um, the reason I asked that question is because of the value that is printed here. This. So we know this is the address of where we are reading our input, right? So that means this is basically the stack pointer. Okay. So the stack pointer is at this address. And so if we add 144 bytes, then we get to the base pointer. And we are adding because if you check the stack setup, like now, for example, if you check func9, 10, you can see it subtracts this value from RSP. So that means if you want to get the value of RPP, we'll have to add and not subtract, you know? Or you could actually run the binary in GDB and then see how the stack is laid out. And then do the calculation. Like now, for example, let's see if, so let's execute till we get the address. So I believe, yeah, so this is the address, right? DE80. So that is the address that we're given, right? Then from the stack, let's scroll up. Yeah, so this is our stack. Okay, so where is E80? E80 is, I think we should check at this point, because one sec. Okay, E80, what the hell is that? There we go. So as I said, this address points to the stack pointer. And since the stack pointer was subtracted from the base pointer, then you add the value in order to get the base pointer, right? Because here's the stack pointer, that's the address that you're given, and here's the base pointer. So you'll have to add in order to get the address of the base pointer, if that makes sense. I hope it does. Um, Also, let me get my keyboard. I've just realized I'm just using my keyboard. Okay, great, cool. So we have this address, so we can grab it. So we can say maybe, I don't know, can have like leak, and then we have like, we can do a receive until, so I can do here like this. So this means we're receiving until we get to this point. And then now we want to grab the address. So we do like, let's do RBP. Okay, we know it's RSP, but normally like I assign the variable that I'd want in the end because I'm going to add the value. So we do like receive line, and then we have to, because now that's a string, but let me add s here. So now we convert it to hex and then add 144 bytes. So if we print this out, uh, RBP, now this is the value of RBP because we've added, so we got the leak and then we added our 144 bytes. And so this is our RBP, which is good. So now let's talk about the buffer overflow. Okay. So first things first, as per the calculations, we know that our buffer sits at 0x98 bytes away from the return. The 0x98 bytes, was it like 152 or? Yeah, exactly. So our offset to the return is 152. But we are not getting to the return first. We are playing with the RBP because if the RBP sits before the return, then there's no point of reading up to the return because the program will fail. Because at that point you'd actually, so like if we do like buff equals to a times 152 and we read this into the program, then the return address would at some point the return address would be 0x41414141, and that's not what you want. So we'd have our 144 bytes. Okay, so at this point now, the next value we'd be writing on the stack is the RBP. Okay, now do note the value that we had here is the RBP of the current stack frame. And as I said, as much as we are giving it the right RBP, we are giving it the value of RBP, not the current value of RBP. Like its value, like RBP is somewhere. Like RBP is what? RBP is like a box, and we want to give it like the value that's inside the box. So we do like RBP plus. So now, then again, you have to check so one detail that I missed is, okay, let's break at func10, run, stack. So this is RBP, right? And you can see it holds this value. And like I said, this value is the RBP of the previous stack frame, so func9. So you can just calculate the distance between the current value of RBP and the value that it holds. Okay, so if you do the subtraction, you'd realize that it's 20 bytes. Okay, so we'll do RBP plus OX20. So that is the value we are giving RBP, as in that is the value that is there. But like since you're messing with a stack, then we have to place everything as is. Like we're not giving it this, we're giving it its value, like its actual value. Like what value is it? Yeah. So I mean, not what value is it. It's more of like what value does it have, or what's its value. Ah, man, this challenge. Okay. So the other thing I mentioned was the return address sits at RBP plus 8, right? So this is RBP. So that means we are placing the return address to func9 right here. So now here is where we place the return address of func9. So you can go to Jidra and copy this. This is the return address that it expects, you know? Okay, so just get rid of this. And we can even have notes. We can say this is RBP func9, and is the return to func9, at least so that, like we stay in check. Okay, then the next thing you notice, so we are right here, right? We've given it this value. And then here, we've given it the return address. So like we are giving it values. I think now this makes more sense. Like this is the RBP, but we've given it this value. And this is RBP plus 8, we've given it this value. I hope that makes sense. But then, before we get to here, which is, no, no, no. Before we get to here, which is here, there is this 2 bytes of junk. Like this is just like useless, like as in this isn't important. And they're like 2 bytes, okay? So we can do like 0 times 2. So that means we've passed 0, like, let's see, we've passed a byte of 0 2 times so that we fill this. Like we're just trying to fill this portion before we get to this, to this bit, if that makes sense. Okay. So we can comment this out and say this is junk. And so the next thing we pass on the stack again is this times 2. Because so now what you're passing is, so at this point we were here, right? And the value of this was this. So it was this plus 20. And now we're here. And the value of this is this plus 40. You know, I hope you're following. That's why I did times 2. Good. So this is RBP in func8. And then it expects the return. So the return, let's just check func9. So we have this. Okay. So this is the return to func8. Okay. And again, the 2 bytes of junk. So times 2. Because now we're here, so we are giving it this 2 bytes of junk. So junk. And then times 3, and so on and so on. So that's pretty much what you're doing. So like, this challenge wasn't hard. It was just like kind of just placing things where they're supposed to be. So are we supposed to be? Yeah, it's this one. Okay. So this is the return func7, and 0 times 2 is just junk. Okay. We are cruising. And so this is OX20 times 4. So this is RBP in func6. And its return address would be in func7. So you copy that. And I'll actually show you how this looks like so that it makes more sense, Func6, and then the junk, and you go on. So it's 20 times 5. There's a cleaner way to do this, but I don't use flat. Okay, so if you watch the walkthrough that I placed here, I think you can come up with your own cleaner solution, like without having to do this. There's a way he did it. that was using pawns flat function to like place things in the stack as they should be. So yeah, but there's how I did it myself. So the return address that would be in func6. So we copy this, put it there. So this is the return func5. Put the 2 bytes of junk, and then times 6. This is RDP in func4, and its return address would be in func5. So go to func5, copy this, ret func4, 2 bytes of junk. See, like it was like a fun challenge, like you just copy stuff and nothing too complicated. So this RBP OX20 times 7. This is RBP in func3. And then its return address, which would be in func4. So put func4, this, return func3, 2 bytes of junk, then times 8. This is RDP in func2, and then its return address, which would be in func3. So you copy this, it's just copy pasting. Man, it's nothing hard here. So junk. I was about to say func. Hello. So times 9, RDP func1, uh, then the return address, which would be in func2. So we copy this, let's func1, 2 bytes of junk. So at this point we're in func1, okay? Because you can see I said the return to func1. So like the minute it jumps to this address, we're now in func1. Then this junk is just junk we are placing in its stack frame. So like this is RBP, right? This is RBP. RBP plus 8 is the return. Then we were talking about the junk, like the 2 bytes of junk. So in this case, this junk, the 2 bytes that we are calling junk, are in func9 stack frame. Okay, like we need them in func9 stack frame. Like we're filling them inside func9 stack frame. So think of it this way. This is like the border, okay? Because this is where we have the return to func9. So think of it like this. And then this is another border. Let's sort of, because, well, okay. Well, I mean, okay, cool. So this is a border. And this is now the contents inside func9. Like this is func9 stack, literally. And then this is its RBP. So yeah, that's pretty much what it is. So that's what I mean when we place the return to func1 here. It's returning to func1 at this point in time here. Okay, then the junk here is inside func1. So literally, if we do stack 70, so you see here. So this is the return to func1, right? You can see for 1 AB3 and we have for 1 AB3. So after for 1 AB3, after the return to func1, we have junk here, right here. We like this is junk, So that's what we are filling in. Okay. So we fill in these 2 bytes of junk, and now we're here at main, I guess. Actually, this is more of like 3 bytes if you think about it. Oh yeah, this is something I was to talk about, but anyway. Um, yeah. So return to func1 junk, and so we are now placing the return address of main, which would be in func1 now. So we copy this. So this is what? This is ret to main. So now we are returning to main. Okay. As much as we are returning to main, there's just one thing that you should note. So to do this as main, you can see, so main returns here, right? Because this is where we do the call func1. So func1 returns here. Wait, did I say main returns here? I meant func1 returns here. So this is where func1 would return to inside main. So it does a move 0 into EAX and then does a pop RBP. So that is something that you should have, you should like have watched out for. Because if you now decide to place the address of the win function right here, like here you do the target.sim win, it wouldn't work because now we are inside the main's stack frame. And so if you're inside main stack frame, when it does this pop RBP, it will pop this value, the address of win, inside RBP. And so the return would just return like the program would exit just normally. So there isn't much that we have done. So since it does a pop RBP, and the RBP, we don't really care about it. So you can just put a 0. You can just put a 0 here, like that. So now when it does the pop RBP, it will just pop 0 into RBP, and we're good. Yeah, so that was pretty much it. I hope we've put everything as it should be, I think. Yeah, so you can see like this was the solution pretty much. So like I know it's long, but you can see like it's nothing hard. It's not like it's like you're doing math and yeah, so yeah, but then again, I feel like we didn't put the RBP of main, did we? Because I'm saying like this is RBP func2, ret func2, RBP func1, ret func1. Yeah, I guess we didn't need it at this point because it's okay. Because this was the RBP to func1 because func1 needed RBP. Because if you check func1, uh, when func2 returns, it executes this function. I mean this instruction. And this instruction relies on RBP. So that is the reason we have RBP here. So this is okay, return to func1. So the RBP is okay. Then we pass in junk inside func1. Then pass in the return address back to main, and then the pop RBP, and then yeah, it's okay. So you can just do send line after. So at this point is where we're passing our input. So you can just do like column space and then pass in our bar, and then go into interactive. Okay, so let's run this. Invalid ret. This we made a mistake somewhere, and I had that gut feeling. Okay, so let's see. 5, 6, 7, 8, 9. Mhm. Okay, I think the best way to do this is actually to just debug it in GDB. So can do like break func10, continue, debug, target.path, and yeah. Okay, so let's see how this looks like. Okay, so now we are in func10. So this is printing the the stack pointer. Okay, then it's writing out tell me about the stack. Then it's reading the 512 bytes, and then now we are returning to func9. Okay, so we go on to func8, func7, func6, func5, func4, func3, func2. Yeah, so in func1 we made a mistake. So if I check RBP minus 8, it's saying it's 0. So it wants the, oh yeah, so it wants the RBP. It wants which RBP? Is it the RBP in main? I guess. So this chal is confusing to some extent. So I think after the junk, we need RBP again. So it's 20 times 10. So this is RBP main. Yeah, that should be good. Because the reason that is there is because the reason we forgot. So because so again at this point we're returning to Func 1. And then this is the junk we're placing on the on the stack inside Func 1. And then so if we check Func 1, there's a leave ret. So remember, like I said, it will what's it called? It will it will move RBP into RSP, pop into RBP. So if we don't have this, then we fucked up the ret to main ideally, because like I said, ret comes at RBP plus 8. So if you don't provide the proper RBP here, then the ret also is fucked up. But for this one, the pop RBP that is happening inside main doesn't really matter because we're not using it anywhere else. So we'll just place a 0 and then return to win. So let's see, this is okay now. Oh. Okay, so func 10, return to func 9, func 9 returns to func 8, func 8 returns to func 7, func 6, func 5, func 4, func 3, func 2, func 1, main, return to win. So now we're in win. Awesome. Yeah, so that's pretty much it. So now if you check, so you see like this pop RBP. So if you check RBP, it's 0, and that's exactly what we wanted because we're not using RBP anywhere else really. Because even in win, it uses RBP, but you can see it's it's moving 0 into RBP minus 8. So like it doesn't really matter to be honest. So let's have process run this, get a shell. Awesome. So that means we can run this on remote. So let's see, challenge, launch instance. Oof. But you should also watch his walkthrough. Maybe he'll explain something that I haven't explained properly or something that I missed. So it's cool. So let it spin up. I think the VM is still live. Nice. So I said spawn the instance and connect to port 9001. So you copy the address. So you have it there on the port 9001. Down this. Awesome. Ls part flag.text. Oh, typo. Yeah, so nest, nest, nest. Too many bloody birds. Because it's nested. Get it? Anyway. Yeah, that was a challenge. It wasn't too bad. It was good. It was good. Personally, when I did it in the CTF, it was fun. Yeah, it was kind of fun. Uh, yeah. So yeah, any questions? I know, I know it has been a bit confusing, but you'll get used to it, I guess. So, any questions? Oh, okay. So we can stop the instance and maybe close GDraw. You guys don't have any questions at all, or you don't know what to ask. Okay, cool. So yeah, I'm gonna upload this recording to YouTube, and yeah, I'll see you guys on B-sides. I told guys I'm going to reuse Intuition and it was Intuition and which one? Intuition and Blindfold from Shehacks. I'm going to reuse them in B-sides, and you guys thought I was joking. I'm not joking. You'll find those challenges there. Trust, I swear, trust you me. You'll find them there. So just try them out, see if you can get the solution so that when B-sides comes, free points, free points. So yeah, cool. Okay. Cheers. Yeah, I hope you learned something and I'll see you guys next time. Peace. Peace out. Cheers. Bye.
Thanks, bro. See you at B-sides.
Yeah, for sure.